I am Dr. Malay Krishna Dutta, Assistant Professor of Department of Physics. My today's lecture is on Green's function. Green's function. Today we will discuss on Green's function. A basic introduction of Green's function. A basic introduction. And its application to solve non-homogeneous differential equation. As an example, we will take Poisson's equation. First of all, we will discuss the homogeneous and non-homogeneous differential equation. So, our differential equation, may be homogeneous or non-homogeneous. Our differential equation may be homogeneous or non-homogeneous. For example, Laplace equation. Laplacian operator phi equal to 0. Phi is any scalar function. This is called Laplace equation. As right hand side is equal to 0 and not function of independent variable. Here independent variable means x, y and z, because Laplacian operator equal to del 2 del x2 plus del 2 del y2 plus del 2 del z2. The independent variable are x, y and z. So as right hand side is 0 and not constant and not function of independent variable x, y and z, so this equation is homogeneous. But instead of Laplace equation, if we consider Poisson's equation, Laplacian operator phi equal to minus rho by epsilon 0. Phi is called scalar potential. And rho is the charge density. So this is an non-homogeneous by inhomogeneous equation, because at the right hand side this is non-zero and this is a function of x, y and z. So this is non-homogeneous equation and this is a homogeneous equation, and Green's function is used to solve non-homogeneous partial differential equation. Achha. Again, a boundary. We have said that a differential equation may be homogeneous and non-homogeneous. Similarly, boundary condition boundary conditions may be homogeneous or non-homogeneous. May be homogeneous or non-homogeneous. Sometimes we have homogeneous differential equation. Homogeneous differential equation with non-homogeneous boundary condition. Homogeneous differential equation with non-homogeneous boundary condition. Homogeneous differential equation with non-homogeneous boundary condition. Homogeneous differential equation means right hand side will be equal to 0 or not function of independent variables, and homogeneous boundary condition means at a particular value of independent variable, dependent variable will be equal to 0, and non-homogeneous one at a particular point of independent variable, dependent variable will be equal to non-zero. As for example, let us consider an homogeneous differential equation L f of x, this is equal to 0. This is a homogeneous differential equation because L is a differential operator. L is a differential operator, linear, suppose linear differential operator f of x is a function of independent variable, function of x, and right hand side 0. This is a homogeneous differential equation. And the boundary condition is that boundary condition y equal to alpha at x equal to a and y equal to beta at x equal to b. Y equal to alpha at x equal to a and y equal to beta at x equal to b. This is the boundary condition, and this boundary condition is non-homogeneous because the value of dependent variable is equal to non-zero at a particular point of independent variables. Now, introducing a new variable, we can transform this homogeneous differential equation with non-homogeneous boundary condition into a non-homogeneous differential equation with homogeneous boundary condition. And Green's function is used to solve non-homogeneous differential equation with homogeneous boundary condition. For example, let us introduce a new variable u of x. This is equal to y of x minus v of x, and the condition of v of x is that v x equal to A, V at x equal to A, this is equal to alpha, and V at x equal to B, this is equal to beta. Therefore, U at x equal to A will be equal to Y at x equal to A minus V at x equal to A. This is equal to alpha minus alpha. This is equal to 0. And similarly, U B, this is equal to Y B minus V of B. Y be equal to beta minus beta. This is equal to 0. Therefore, L equal to Lyx. So therefore, from this equation, Yx will be equal to U of x plus V of x. So therefore, U of x plus V of x, this is equal to 0, or Lux equal to minus V of x, this is equal to fx. Lux equal to fx. So this is an non-homogeneous differential equation. Lux equal to fx, non-homogeneous differential equation with homogeneous boundary condition that U equal to 0 at x equal to alpha and U equal to 0 at x equal to beta. Green's function is used to solve this type of non-homogeneous differential equation with homogeneous boundary condition. This function f of x, this is called source function or source term. Now we will introduce Green's function for one-dimensional case. Green's function for one-dimensional case. Green's function for one-dimensional case. Consider a non-homogeneous differential equation. Let us consider a non-homogeneous differential equation f of Ly of x, this is equal to f of x. Ly of x equal to f of x. This is no relation between this y and this y. Just in general, Ly of x equal to f of x in the interval a less than equal to x less than equal to b. With a specified function, specified known function with a specified known function f of x. This is called source function, so known as source function. Suppose this is our equation number 1. The boundary condition are that boundary condition boundary condition on y are specified at x equal to a and x equal to b. These are the two limits of x, lower limit equal to a and upper limit equal to b. So boundary condition are specified at x equal to a and x equal to b. And to solve this non-homogeneous differential equation, we introduce a Green's function. To solve one, we introduce a function capital G x comma t WHERE, where t less than equal to b less than equal to a, and this function gx comma t called Green's function. Calls Green's function. So we want to mention again that to solve a non-homogeneous equation, we introduce Green's function, and the independent variable x in the differential equation, the range of the a and b, and the Green's function will be function of x and t. Green's function will be function of x and t, but t should lie in between a and b. A is the lower limit of the independent variable x, and b is the upper limit of the independent variable x. And there Green's function must satisfy some conditions. Green's function must satisfy some condition. Green's function gx comma t must satisfy number 1, L G x comma t equal to minus delta x minus t. L is the differential operator, and the same operator involving in the original differential equation, non-homogeneous differential equation. And delta x minus t, this is called Dirac delta function. This is called Dirac delta function. And according to definition, this is equal to 0 except at x equal to t. x0 at except at x equal to t. And second condition, g x comma t must satisfy the same boundary condition, at x equal to a and x equal to b. Then the solution of the equation 1, of 1 will be y equal to minus a to b g x comma t f of t dt. This is the beauty of the Green's function, because if we find we can find a Green's function gxt for a given differential equation for a given boundary condition. Then with the known function of f of t, we can find the solution of the non-homogeneous differential equation in this form: yx equal to minus a to b gx comma t f of t dt. As ft is known, so to find the solution of non-homogeneous differential equation, basically we need to find the Green's function gx comma t. And now we will show that why we can write the solution of the non-homogeneous differential equation in this form. And this proof is here, proof. Why we can write the solution of non-homogeneous differential equation in this form: L y of x equal to minus L a to b g x comma t f of t dt, or minus a to b L g x comma t f of t dt, or minus a to b delta x minus t f of t dt, or this is equal to minus, so minus minus plus, and according to the definition of Green's delta function, this will be equal to f of x. So y x equal to this minus a to b gx comma t f to dt. This is the solution of non-homogeneous differential equation L f of x, L y x equal to f of x, which was denoted by 1. And another important point is that Green's function g x comma t must be continuous in the interval a less than x less than equal to b. This must be continuous in the interval. Now we will show that how Poisson's equation can be solved with the help of Green's function. Solution of Poisson's equation with Green's function. Solutions of Poisson's equation with Green's function. So Poisson's equation is that Poisson's equation is Laplacian operator of phi equal to minus rho r divided by epsilon 0, Laplacian of phi equal to minus rho r by epsilon 0. Phi is the electrostatic potential, function of x, y and z. X, y and z are independent variables. Rho is the charge density, and epsilon 0 is the permittivity of free space, permittivity of free space. And now we have a boundary condition. We have boundary conditions. Boundary conditions on phi and its derivative. Boundary condition on phi and its derivative. And we know that the solution will be like this for a single point charge, for a discrete distribution of charge, for discrete distribution of charge, phi will be like this: 1 by 4 pi epsilon 0 summation over qi by ri. Suppose there are Q1, Q2, Q3 number of charges at R1, R2, R3, Ri position, and we want to find the potential due to the whole combination of discrete charges at a particular point. Then the potential phi will be equal to 1 by 4 pi epsilon 0 summation over I equal to 1 to n. If there are n number of charges, I equal to 1 to n Qi by Ri. And in case of continuous distribution of charges, phi equal to 1 by 4 pi epsilon 0 integration rho d tau divided by r. Now, if the charge is at position R1 and we want to find phi electrostatic potential at R2, then phi will be 1 by 4 pi epsilon 0 integration rho d tau divided by R2 minus R1 integration over the volume tau. So for a continuous distribution of charge, solution of Poisson's equation will be like this, and for discrete distribution of charge, solution of Poisson's equation will be like this. Now, with the help of Green's function, we will show that solution of Poisson's equation can be written in this form. Solutions of Poisson's equation can be written in this form: phi equal to 1 by 4 pi epsilon 0 rho d tau by mod R2 minus R1 integration over the volume tau. For this, suppose we can show this with a diagram. Suppose this is a coordinate system. This O, this is X, Y, Z at a particular point R1. This is your source point. At a particular point R2. This is observation point, and this is R2 minus R1. This is equal to R21. or R12 or R12. So Green's function G R1 vector R2 vector must satisfy Laplacian operator G R1 R2, this is equal to minus delta R2 minus R1. Previously we have shown that the L f of x equal to yx, then Laplacian operator of G x comma t equal to minus delta x comma t. So these two operators are same. So in the Poisson's equation we have Laplacian operator in place of L. We have Laplacian operator as a differential operator. So Laplacian operator of G R1 R2 will be minus delta R2 minus R1. And according to the definition of Dirac delta function, delta R2 minus R1, this is equal to 0 if R1 not equal to R2, this is equal to 1 if R1 equal to R2. And integration f R2 delta R2 vector minus R1 vector delta over the volume tau, this will be equal to 1. This will be equal to of f R1. Now we show that the solutions of Poisson's equation with the help of Green's function can be retained in this form. And physically G R1 R2 is the potential at a particular point, due to a unit charge, is the potential at a particular point due to a unit charge. And from the Green's theorem, we have phi Laplacian operator of G minus capital G Laplacian operator of phi d tau integration over the volume tau. This is equal to phi gradient of G minus G gradient of phi dot ds integration over the surface S. From the Green's theorem we have, so phi is a scalar function and G obviously a scalar function. And in the case of Poisson's equation, if we assume that phi is the electrostatic potential which varies as 1 by r, and Green's function and Laplace gradient also varies as 1 by r, and G is the Green's function due to unit charge, so this is also varies as This is a potential due to unit charge. So this is also varies as 1 by r. So this term varies as 1 by r cube, and the surface term varies as r square. So basically phi gradient of g ds or g gradient of phi ds, both the term varies as 1 by r. And if we take the surface as infinity, so the radius r will be infinitely large, then this term will be equal to 0. So we obtain gradient or integration over the volume tau phi Laplacian operator of g equal to integration g Laplacian operator of phi d tau. Phi Laplacian operator of g d tau equal to g Laplacian of phi d tau. Then integration over the volume tau phi Laplacian operator of g means minus delta r2 vector minus r1 vector d tau. This is equal to integration over the volume tau g, and from Poisson's equation Laplacian operator of phi equal to minus rho by epsilon 0 d tau. So minus will be cancelled from both sides, and using the definition of Dirac delta function, this side will be gives phi r2. This is equal to 1 by epsilon 0 integration over volume tau g rho d tau. Now rho is known for its Poisson distribution is known, so source function rho is known. Now the task left is that we have to find the Green's function g to solve Poisson's equation. So this is the solution of Poisson's equation, and the task left is that we have to find the Green's function g, because rho is known to us, and we know that it is well known that integration over the volume tau Laplacian operator 1 by r d tau equal to 0 if origin is in the volume, is not included in the volume, and this is equal to minus 4 pi if origin is included in the volume. Or integration over tau Laplacian operator 1 by 4 pi r d tau equal to 0 or minus 1. 0 means just we have taken 4 pi from left side and divided the whole thing by 4 pi. So 1 by 4 pi r d tau equal to 0. So Laplacian operator 1 by 4 pi r delta tau equal to 0 if origin is not included in the volume, or equal to minus 1 if origin is included in the volume. So using the definition of Dirac delta function, we can write Laplacian operator of 1 by 4 pi r, this is equal to minus delta r. And so Laplacian operator of 1 by 4 pi r 1 to equal to minus delta r2 vector minus r1 vector. Again, we know that Laplacian of operator Green's function g r1 r2, this is equal to minus delta r2 vector minus r1 vector, and comparing this equation we can write Green's function g r1 vector r2 vector equal to 1 by 4 pi r12. As we have said earlier that the solution of Poisson's equation phi was phi equal to 1 by 4 pi epsilon 0 integration g rho d tau, and g come out at 1 by 4 pi 1 by epsilon 0 1 by epsilon 0 integration 1 by 4 pi r12 rho d tau. So 1 by 4 pi epsilon 0 integration rho d tau divided by mod r2 minus r1 vector. So this is the solution of Poisson's equation with the, as we have said earlier, and we can find it with the help of Green's function. That is all for today, and this is the technique how Poisson's equation can be solved with the help of Green's function.